Assalamu alaikum, guys. In the previous lecture, we have discussed about the sampling, where we multiply the signal by a terrain of pulses, right? So this is another different. Like in this lecture, we will actually look into different technique of sampling, which is called pulse amplitude modulation. Pulse modulation, or PAM. So in our previous case, what we did, where we actually used terrain of pulses, in that case, actually what we did, we actually have impulse based sampling, right? In the previous cases, we have impulse based sampling. So in impulse based sampling, we have impulses at every TS, the terrain of pulses with a impulse duration TS. So this the signal is actually multiplied with a terrain of impulses. So in impulse based sampling, the amplitude of the impulse is actually scaled by the amplitude of the signal. So it becomes the impulse at 0 becomes m of 0, impulse at TS becomes m of TS, impulse at 2 TS becomes m of twice TS, so on and so on. So it's actually impulse based sampling. So impulse based sampling. So in the previous cases, we actually talked about the impulse based sampling. Now we want to, instead of impulse based setting, we actually we want to, this is actually impulse. We have to do sampling by pulses, not impulse. Okay, so this is actually impulse based sampling. So let's see what we can do by sampling by pulse based. So let us say we have a signal, and rather than having a impulse, we have a pulse. Okay, so for a signal, we have, instead of pulse impulses, for example, this is actually impulses, right? At that moment. So instead of impulses, we will have pulses. Okay, pulse based sampling. So in pulse based sampling, for example, at 0, so we will have a pulse. We will have a pulse. And this pulse will have a duration. So pulse have a duration t. So at TS, for example, at TS, it will have a duration t. So it will be TS plus t. So at this moment, it will have twice TS. Which is actually, the duration is twice TS plus t. So t duration, same thing. so on and so on. Okay, so in this was a impulse based sampling. So in pulse based sampling, instead of impulses like this, we have a pulse with a finite duration, which is actually t finite duration. And when we multiply this impulses with a signal, then this amplitude of this pulses will be scaled by the amplitude of the signal, which is actually in our cases this signal. Okay, so this is actually, so here what we can say that here the sampling frequency is fs. If this is the case, then sampling time for duration is ts, which is nothing but actually 1 by fs. So what here we are saying that the sampling will be sampling using pulses instead of impulses, pulses of duration t. So this is actually t duration. Everyone is t duration. This is also t duration at each nts. Okay, n varies for example, one is infinity to plus infinity. So what we are saying that instead of using impulses, we are using or we are considering pulses, and the when we are using impulses, or rather using impulses when we use a pulses of duration t, the pulse amplitude will be scaled up by the sampling sampling signal, okay, or our signal which we want to sample. Okay, so for this case, the nth pulse is from any signal from 0 to ts plus t. So the nth pulse will be from n of ts to n of ts plus t, because each pulse is t duration. So the amplitude, so at any moment, amplitude of the pulse at nts will be actually the value of signal at nts, value or amplitude of signal at mts, value of signal at m of n of ts, right? Same as the previous one. So at any moment, the amplitude will be by the m of ts, that amplitude. For example, this is the amplitude here. This is the amplitude here for this signal. This is the amplitude of this signal. This is the amplitude of the signal. Okay. So actually this one, this is the amplitude of this signal. This is the amplitude of the signal. This is the amplitude of the signal. This is the amplitude of the signal. So at amplitude of the pulse, this amplitude of the pulse, this amplitude of this pulse is, what are we saying, at nts or any at nts. For example, this is the nts to ts, which is the value of signal at m of nts, the value of signal at m of nts, which is actually m of that signal, m of nts. This was twice ts, so m of twice ts. That was the corresponding value. Okay. So we are sampling the signal at each NTS and holding for a pulse duration T. That's actually we are seeing here, right? So we are actually sampling at MNTS, for example, for this one MNTS, and we are holding it for T duration. Previously, it was an impulse, like momentary. Now, instead of momentary, the pulse duration becomes T. Okay, so it has a it has a means at that moment the pulse amplitude is holding for T duration. Okay, the amplitude duration. So what we are saying that for example, sampling signal at each NTS and holding for duration T. That's why this mechanism, amplitude modulation, is also called sample and hold. So what we are saying that sampling at each NTS and holding the sample value for duration or constant value constant for duration of T. That's why this mechanism is also this amplitude modulation. This mechanism is also called sample and hold mechanism. Sample and hold. So amplitude modulation technique is also called sample and hold technique. Okay. For this sample and hold, the the duration of the T duration, the sample duration. Okay, it was a sample here, and it will hold for T. This will be this T duration should be much lower than the TS. Where is the T is the pulse duration, right? This is the pulse duration. This is the pulse duration. And this TS is the sampling interval. Sampling interval, which is actually in our cases this one, sampling interval. So 0, then TS, then twice TS. So these are the sampling interval. Each one is right. The next one will be like, so this is actually TS. So this is actually TS. So this will be also TS. Same thing here. This will be the TS. Okay. So the pulse duration should be much lower than the sampling interval. Okay. Now, as the pulse is relatively small portion, this pulse, this T is relatively small compared to the sample interval, the smaller the duration of the pulses. If this pulse duration, if this duration gets smaller, okay, so more precise the sampling will be. For example, this one, this is the duration. Imagine this duration is no more like this duration. Imagine this duration. You see, when we take much longer duration, right? Here, this is also this value, but by this time the signal value changes. So this is the like this small portion is the error here. But instead of if I choose the sample duration this t small, what will happen? I'm picking every changes, right? I'm picking every changes. You see, I'm picking every changes here. I'm picking every changes here. I can detect every change. I can detect these changes, these changes. But if it becomes longer, then I miss that changes. Okay. So the smaller push is the sampling interval. Then the pulse, smaller the pulse duration, more precise will be actually the sampling. So the pulse is simply spreading the value of signal over that duration of time. Here, like this pulse will spread the value of signal over duration of t. So we can say what is actually happening is that the pulse is simply simply spreading the value of signal over duration t, over duration of t. And also pulse is confined to a relatively small portion of the sampling interval. So smaller the duration of the pulse, more precise the sampling. That is also true. So what we can also say that smaller the, so what do we say, the pulse is confined to a relatively small portion of sampling interval and smaller the duration of the pulse smaller the duration of pulse, the more precise sampling is. So this is actually the PAM, pass aptitude modulation, also called sample and hold, or this is also called flat top because it makes the flat of the pulses, like top of the pulses flat for the region of T. This is also called a flat top. This is also called a flat top pulse. This is also called a flat top sampling because this is employing, so PAM employs flat top flat top pulse, which is also termed as flat top sampling, also known as flat top sampling. Okay, so we already have the idea about pulse amplitude modulation, which is also called sample and hold, and flat top sampling. Okay. So we are modulating the amplitude of each pulses at NTS, that is scaled by the value of the signal at NTS, or which is actually NTS. times the pulse, that is each pulse is in unit amplitude. Okay, so let us say, so if so what happens in in pulse amplitude modulation, we are actually having these pulses, right? So this is, we are having these pulses, right? Let us draw this sampled pulse. Let us draw the sampled pulse. For example, say this is sampled pulse. Okay. So at m0 of at 0 corresponding m0 corresponding signal, this is called m0. So another one may call ts at ts, right? At 0 at ts, they're called m of ts, right? So another at twice ts, each one having its t, t of duration, m of twice ts, like this. So this is actually our PAM signal, representation of a PAM. This is actually representation of our PAM. So this is actually terrain of pulses. So the amplitude of pulse at NTS. So what we can say, the amplitude here, what is happening? The amplitude of pulse at n of NTS, is modulated by signal value NTS, right? That's why you see this pulse terrain, this was actually unit amplitude pulse, right? You see how we end up with this PAM, these pulses, right? So this is actually nothing but that, like you had a amplitude like signal, you had a signal, and you had a unit amplitude pulses, like unit fixed amplitude unit amplitude pulses, a terrain of unit amplitude pulses, terrain of unit amplitude pulses, terrain. When they are uh, multiplied, then this terrain amplitude pulses, the amplitude of these pulses, actually they are scaled. They are scaled by this amplitude of, for example, 0 at ts, at twice of ts, which is actually like, for example, 0 at ts, at twice ts. They are scaled by the amplitude of the signal. Scale by the, so what we are saying, this scale by m of nts, right? This pulses is actually scaled by the. So what we can say, this this PAM, we can actually write this signal as like this. So we can write this signal, this pulse amplitude modulated signal as m of nts multiplied by the unit amplitude of pulses, right? Pulses by pulses, p t minus nts. These pulses, they are shifted to nts, right? This is actually a pulse shifted nts, shifted to pulse shifted to nts, right? Each time this sample is goes to, like, from 0 to TS. So it's actually shifted. This pulse actually shifted from 0 to TS, TS to twice TS. That's actually NTS actually. That's actually it means. If it's 0, then it's PT at 0, PT at 2, N minus twice TS, N minus like 1 T minus TS. So which is actually this one. At 2 is T minus twice TS, T minus twice TS, this one, this pulses. So this pulse, so this pulse will be multiplied with this portion of this this amplitude of the signal. This pulse will be multiplied with this portion of the signal. This pulse of the pulse with its amplitude will be multiplied with this portion of the signal. You see? So MNTS into, so this will be the modulated pulse amplitude modulation. This one is represented by this equation. Okay. Now this is actually pulse amplitude modulated signal. This is actually pulse amplitude modulated signal. This pulse amplitude modulated signal. Okay. Now what we find so far, that pulse amplitude modulation is known by other terms, right? So it's a sample and hold and flat top sampling, right? Okay. So how about the pulse? Let's see what is this unit amplitude pulse? This is actually the pulse, right? Let's see how can we characterize it. So we can characterize it by this way. This is a pulse which have a duration of t and this has a unit amplitude. So this is actually the pulse PT, pulse of PT, right? Which have a duration of what? T, and it has a height. We say it is a unit amplitude, height 1. So PT can be expressed as two-way, right? Its value is 1, amplitude 1 for what? If its duration is 0 to, like T is 0 to T, from 0 to T. Otherwise, its value is 0, means here is value 0, here is also its value 0, means otherwise. That's actually the how we characterize this pulse. Okay, now so we can see that for nth sampling, for n sampling time, we have a MNTS multiplied by the pulse shifted by NTS, right? That's actually we are seeing here, that nth sampling time, we have MNTS, which is a portion of the signal at nth sampling time at any moment, which is actually that portion of the signal, either here, whatever. It depends on the value of n, right? Nth pulse, nth sampling. So 0, 1, 2, 3, 4, 5, like 0 second, first second, second second, third second, fourth second of sampling, right? Is multiplied with the pulse, which is actually shifted to the NTS. Okay. So doing like if we do to the impulse sampling, like ideal sampling, if we compare, where we at the impulse shifted to the NTS, right? What happens? Like here it has a width. What compared to the impulse sampling, where the impulse is actually shifted to every NTS, right? Scale by of the signal MNTS. That's actually, instead of that, we have actually pulses. Instead of impulses, we have pulses. Right? If we compare the previous cases, right? If we compare to the previous cases, it's actually the impulse is actually shifted to the replaced by the pulses, right? So what we can say that what is the pulse amplitude modulated signal, PAM? What is the pulse amplitude modulated signal? So pulse amplitude modulated signal M of MP, MP of T. Pulse amplitude modulated signal can be expressed as nothing but the value of n minus infinity to plus infinity, and we know actually this signal, pass this signal, the whole signal. We are writing it as a modulated signal, that M of NTS multiplied by this pulse P shifted to NTS. Okay, this is modulated signal. So which have depend on the a value of n, this value changes. Okay, so this is actually the complete the series of pulse modulated signal. Okay, so this is actually the complete. If you add the summation of n minus infinity plus infinity, you actually creating this whole like this one for n equal to 0, n equal to 1, equal to 2, all this blah 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 blah. Right? Okay. So MPT. This is how we actually express our pulse amplitude modulated signal. Okay, like pulse stream of the pulses. Now, at every NTS, for every NTS, we can think of. Let us think of this signal. How this signal was created. So this is actually this one. This signal is actually pulse amplitude modulated signal, which is actually expressed by this equation. And if we complete or add up all these pulses, this is for individual pulses, right? This one is actually for individual pulses. If I add all the pulses, by this equation, summation of this equation, we actually end up all this stream of this signal, all the signals, stream of this signal, all the signal, right? Now, this signal, which is actually here, we can think of it as a like original impulse stream convolved with the pulse. Like how, for example, this signal can be, we can think of, right? That how we can, other way we can have these pulses. We can think that this is the original impulses. Like this was the impulse. This is an impulse. This is an impulse convolved with the pulse. Convolved with the pulse to create this pulse. Okay. So what we can say that, okay, this equation, how can we can think of other way that how this equation was generated? We can say that, okay, it can be represented as, okay, we have a impulse convolved with a pulse. We have a impulse convolved with a pulse. We have a impulse convolved with a pulse. So this can think of that original impulse stream. So this was the impulse stream, right? So you see, these are the impulse stream. These are the impulse stream. Stream convolved with the pulse, because we have our original stream of impulses. So this signal, so we can say that this one is actually can be written as a impulse sample stream, impulse sampled impulse sampled stream. Impulse sampled stream. You see, these are not the not only the impulse stream. If it would have been an impulse stream, it would have been like impulse, 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 so similar height. Now they are sampled, means actually the height varies depend on the how the signal is varying, amplitude of the signal is varying. So they are sampled. Impulse is sampled by the signal. Okay, so these are called impulse sampled stream, convolved with the pulse. Pulse PT. If you do this, we will end up with this one, which is actually also the PAM signal, right? So if this is the case, if it's an impulse sampled stream, right? What is an impulse sampled stream? What is an impulse sampled stream? We actually find this impulse sampled stream, impulse sampled stream, right? Convolve with the pulse. What is the so let's see, we actually already did in our sampling that when we have a impulse, you see, these are actually ideal impulse, stream of ideal impulse, which actually will be sampled by the varying of the signal amplitude, and we will actually we will end up with the impulse stream. We will sampled stream, right? It is a sample signal, impulse sampled stream, which will be actually expressed by this equation. So this impulse sample stream can be expressed by this equation. We are actually writing the same impulse sample stream here. So which is actually n equal to minus infinity to plus infinity m of n of ts del of t minus nts. Isn't it? Yeah. So this is a impulse. This actually impulse sample stream. Now this impulse sample stream convolved with a pulse PT. Convolved with a pulse PT. If this is the case, then what happens? N of minus infinity to plus infinity m of n of ts. This del will shift this pt to nts, right? So we can write pt minus nts, okay, which is actually our m of pt, which is actually our impulse sample stream. So when we do the impulse sample stream convert the pulse, we actually have the modulated pulse amplitude modulated signal, right? Or pulse amplitude modulated signal, which is actually, you see, this signal, the expression of this one is actually similar to the expression of this one. Like this is how the interpretation is actually. So pulse modulated. So this is nothing but the pulse amplitude modulated signal. We actually have the similar. So this is the expression for the pulse amplitude modulator, how we expressed it or how we understood it actually. Because now what we have seen that in ideal sampling, where we have actually impulses, stream of impulses, which is actually very impractical. So we, instead of that, we actually took a finite duration of the pulses. We actually took finite duration of pulses to modulate the signal, which have a finite amplitude and duration. So the pulse amplitude modulated signal will have a finite duration and finite amplitude. Okay. So rather than ideal sampling, which is very difficult to implement, we actually generated terrain of like instead of terrain of pulses, we actually generate terrain of impulses. We actually generate terrain of pulses, which is actually more realistic, which have a finite duration and finite amplitude. Okay, so this is how the pulse amplitude modulated signal is generated.